Chapter 6, Number 27. Two blocks are connected by a string as shown in the figure. The smooth inclined surface makes an angle of 42 degrees with the horizontal, and the block on the incline has a mass of 6.7 kilograms. Find the mass of the hanging block that would cause the system to be in equilibrium, assuming the pulley is ideal. A couple of important things, maybe start off with the most part. Smooth means no friction, so that would be easy enough. So what we want to do now, they've given us a picture, is we should probably draw some free body diagrams. So we'll start with the block, which I'm going to call M1, and the hanging weight, which I'm going to call M2. On M2, we have a weight pulling down FG2. On M1, we have a weight pulling down, which I'm going to call FG1. Also on the hanging block, we have the string attached. It's going to exert a tension pulling upward, Ft. And because the pulley is ideal and the strings are ideal, that tension will be the same everywhere, which means it's also this pulling on block 1 in the direction of the incline. And then finally, on block 1, we have the surface it's on, the incline itself, which exerts a normal force perpendicular to the incline. For this part of the problem, I'm going to want to use an axis that have maybe x along the incline and y perpendicular. And then for this part of the problem, I'm going to use y vertically and x horizontally like usual. When we do that, we see that our FG1 is actually two different parts. So, slightly different color. There is an FG1X and an FG1Y, where FG1X points down along the incline, and FG1Y points into the incline. We'll probably want to get those components as quickly as we can, so we might as well do that now. So we have FG1, and we have FG1X along the incline, and FG1Y perpendicular to the incline. And then we sort of put the incline back into the picture here, knowing that this angle is theta. Then this angle is 90 minus theta, and this angle is 90 minus 90 minus theta, which is just theta again, as we've done several times, based on the fact that we've got a bunch of right triangles here. This allows us to say that FG1X is FG sine theta, and FG1Y is FG cos theta. All right, we're going to want to go to a different screen so that we can expand on all of this. So give me a second to get there. So from our free body diagrams, we have the sum of the forces on body 1 in the x direction is, and if we look here, we can see that it's going to be Ft and Fg sine theta. But Ft sine theta is going to come in with a minus sign because it opposes Ft and moves in the minus x direction. And then the sum of the forces in the y direction are going to be Fn and Fg cosine theta. But again, the y part is in the negative y of our axes, so it gets an extra minus sign. And then F2y is going to be, well, there's an Ft and an Fg2. But as we're probably getting used to, one of them comes in with a minus sign. And then from Newton's second law, all of these guys are equal to ma, but a is 0 because we're at equilibrium. So I can say that all of these sum to 0. That allows me to put them together as ft minus fg sine theta. Sorry, that's pretty badly written. fg sine theta is 0, and fn minus fg cos theta is 0, and ft minus fg2 is 0. So top guy becomes ft equals fg1 sine theta, which is m1 g sine theta. And third guy becomes ft is fg2, which is m2g, and of course ft is equal to itself. So that allows us to say that m1g sine theta is the same as m2g, and we eliminate the g's obviously, and we get m2 is m1 sine theta, which, checking our problem very quickly, says this is equal to 6.7 kilograms times the sine of 42 degrees, using, of course, that and that, which numerically turns out to be 4.5 kilograms when correctly rounded to the 2 sig figs.